Today we're going to talk about the first of two lectures from chapter 16, and today we're going to talk about the part about oscillatory motion. To oscillate means to move back and forth between two defined points. And when we talk about this, we're moving into a part of physics. Generally, physics is actually divided in two parts in many different ways, and one way in which it's divided into two parts is between particles and waves. Natural phenomena, natural physical phenomena can either be considered a particle phenomena or it can be considered a wave phenomena. And up to this point we've been talking primarily about particle phenomena and the movement of masses, etc. Now we're going to switch and begin to talk more and more about wave phenomena. And this week and next week we will be talking about chapter 16 in that regard. So let's talk first about something called Hooke's Law. And Hooke's Law is a description of the restorative force when a oscillating object is moved off or its equilibrium position. So first of all, what is the equilibrium position? Well, the equilibrium position is the position that an object has at rest when there is no force applied. And so that's what's meant by the equilibrium position. When you move something from the equilibrium position to some other position, that displacement is called deformation. And that requires an outside force. Once deformation occurs, there's a force that wants to return the object to its equilibrium position. And the force that is in effect that wants to return an object to its equilibrium position is called the restorative force or the restoring force. And Hooke's law is the law that describes the restoring force. And written mathematically, it's the restoring force is equal to a minus kx, where k represents a constant subject to whatever material you're working on. K, as I said, is the force constant, and that is a function of the material as well as how the material is made up, or what it's made, whether it's thick or thin, smooth or rough, etc. So when we look at a material moving along this way, you start out, you have a plastic ruler. The plastic ruler has been deformed. Okay, it's moved off its equilibrium position. And once released, the restoring force works to return the ruler to its equilibrium position. When it reaches the equilibrium position, F is equal to 0. However, it has velocity. And because it has velocity, it has momentum and it continues to move. And so it actually deforms again. And it reaches the point shown in figure C. Now at that point, there's another restoring force. And it's in the opposite direction. And it then moves the ruler back toward the equilibrium position. Again, it reaches a certain point and it has a velocity again. And it continues to move back and forth. Now, if there were no friction or other real world things going on, real world forces acting in addition to this force, this would go on forever, back and forth in a perpetual motion. But obviously that doesn't occur. Now another way to look at this is to look at a graph of the mass or the displacement that occurs when you add a mass onto a spring. So you're looking at this diagram here. You have a spring in this position here, and it's at rest in the equilibrium position. And you add a mass, which represents a force pulling it down, and it pulls it down a certain distance x, x1. And then, so you can do a relationship between x1 and the weight 1. And you can graph that, say that this point represents x1 displacement and the mass one or the weight one at this point. And then you add a larger weight and it displaces it more, and maybe this point represents that, etc. And so you can graph this. And so a graph of the absolute value of the restoring force, and that is the weight that you hang on there, is what it would take to pull that back up to the equilibrium position. And that can be graphed against the displacement that occurs. And this graph is generally a straight line. And if it forms a straight line, it means that the system involved is obeying Hooke's law, because Hooke's law describes a straight line, and the slope of the graph is the constant K, the force constant. So the rise over the run, the slope, is the force constant. So you can do this in various ways with different springs, and you get different results. And if the mass has to be stationary in order for this to represent the restoring force. Okay, let's take a look now at an application of Hooke's law. And here we have a back end of a car. We know that the back end of a car is supported by a suspension, a set of springs, and obviously these springs are going to have a restorative force. So when a car is in a certain position, it's in the equilibrium position based on the weight of the car. And if you introduce a passenger, then this causes a displacement of the car on its suspension system. And this displacement is the deformation. And then the other part, or you can calculate what it would require to restore the car to its original position before the person got in. So let's take a look at how we would do that. What is the force constant for a suspension system of a car that settles 1.2 centimeters when an 80 kilogram person gets in? Okay, so the formula is that F is equal to minus Kx. Okay, now if you rearrange this to get K, K is going to equal to minus F over X. And so that's going to be 80 times 9.8 divided by 0.012. And so that's going to equal 0.46 is 78 divided by 0.012. You get 2 or 6.53 times 10 to the 4th newtons per meter. So the restorative force is equal to 6.53 times 10 to the 4th newtons per meter. Looking at this, we are now going to talk about the energy involved here, the work or energy involved, and this is going to be a form of energy called the elastic potential energy. And if you graph the same displacement curve, the applied force versus the displacement, remember the slope of this curve is the force constant. Well, the area under this curve represents the energy or work. And if you do the calculation here, this is the area of a triangle. So the area of a triangle, and you end up doing the math here, and you get 1/2 kx squared, which is the formula you need to remember. Or you can do it with this method. So this is called elastic potential energy, and this is the stored energy in any deformed system that's not in its equilibrium position. And that system has to obey Hooke's law for this formula to be relevant. So this graph here shows the deformation. It's the same graph that we looked at before. And the work done is going to be the area in the curve, as I said. And when you do the calculation here, you end up with 1/2 kx squared. And that's the formula you have to remember for elastic potential energy. So here's another problem we're going to take a look at. Here you have a gun. You load at this point, it's not compressed, so it's in the equilibrium position right here in part A. You cock the gun, and now it's deformed, compressed and deformed, and it's been deformed to distance x. You add the ball or the bullet, projectile, whatever you want to call it, and now there's nothing moving here, so all you have present is the potential energy that is present. When you fire the gun, the potential energy is then converted into kinetic energy. So this elastic potential energy is converted to kinetic energy, and that is in the form of a velocity that this projectile will move in. So if we have a problem, we have this gun. First of all, how much energy is stored in the spring of this gun if it has a spring constant equal to 50 newtons per meter and it's compressed 0.15 meters? Now we'll do this in a second, but you can see that the force here is going to be kx, and the stored energy is going to be 1/2 kx squared. Then, if you neglect friction, whatever answer you get for this stored energy is going to then be converted into kinetic energy to fire this projectile, 2-gram projectile from the gun. So let's look at how we would do that. So the elastic potential energy is 1/2 kx squared, and that's 1/2 times 50 times 0.15 squared, and that's going to be 0.5625 joules. Now that is going to be now converted into a velocity. So if Ke is equal to 1/2 mv squared, then V is going to equal 2 times Ke divided by m in the square root, and that's going to be 2 times 0.5625 divided by 0.002 kilograms, because this is joules, and the square root of that factor right there. And if we do that math, we get 23.7 meters per second. So now let's take a look at some more problems looking at Hooke's law. The first problem, a 80 kilogram man stands on a pogo stick which is compressed at 0.12 meters. What is the force constant of the spring? This is a very straightforward problem. You have F is equal to minus Kx, so that K is equal to minus F over X is equal to minus 80 times 9.8 divided by 0.12, and this is a minus 0.12 because it's being compressed. If you do the math on this one, you get 6.53 times 10 to the third newtons per meter. The second problem says that the springs of a pickup truck act like a single spring with a force constant of 1.3 times 10 to the 5th newtons. By how much will the truck be depressed by its maximum load of 1,000 kilograms? So the maximum load this is allowed is 1,000 kilograms. Again, F is equal to minus Kx. Now we're going to solve for X. So X equals F divided by K, and that's a negative. This is going to be 1,000 times 9.8 divided by 1.3 times 10 to the 5th. And all this quantity is going to be a negative because it's depressed. If you do the math here, you get minus 0.0754 meters or 7.54 centimeters negative, about 2 inches, almost 3 inches. It says if the pickup truck has 4 identical springs, what is the force constant for each? There's 2 ways you could do this. You could just take this number and divide it by 4. Or you could take and divide this and say that this is equally distributed. Put this same formula in here or use this formula actually right here and put in 250 times 9.8 divided by 0.07454. Either way, you get the same answer, and that answer is 3.25 times 10 to the 4th newtons per meter. And so either way, you get the same answer.